So a little reminder of some transformations. That function would be translated right 1 unit and up 2 units compared to your parent function. We're going to look at some of those transformations again today and do some graphing, your favorite. So I'm going to graph 2 times the absolute value of x to start with. So there's lots of ways that you could do this. I'm just going to make a table of values for this one. So if you plug in a good variety of points here, like -2, -1, 0, 1, and 2, absolute value of those times 2 is going to give you 4, 2, 0, 2, and 4. So if you plot those on a graph, if you know what absolute value functions look like, you already knew this was going to make a V shape, and it's not translated left or right, so its vertex is at 0, 0. Looks like that. Comparing to our parent function, well, parent function absolute value just has like a slope of 1. So if I plot my points for my parent function, it's going to look like that. So this one is a vertical stretch by a factor of 2 compared to my parent function. If I look at b, it's going to be translated to the right by 4 units. Or you can think about its vertex is moved to 4, 0. So you could just plug in some points on either side of your vertex and reflect them over to get the full graph. So say that I do like, what's close to my vertex? How about 3 and 2? Don't forget you're doing the absolute values. That'll give you +1 and +2. So it's just your standard absolute value function, except it's translated to the right 4 units compared to your parent function. If you look at a couple more, so this h of x is 1/2 x, 1/2 absolute value of x, minus 4. I'm going to do this in a couple steps here. So if I, again, do, let's just do 0, 1, and 2, because I know it's not translated left or right, so its vertex will be at 0. If I do 1/2 times the absolute value of those, I'll get 0, 1/2, and 1. And then the minus 4 is going to translate it down 4, which means I'll subtract 4 from all of those 1/2 x y values. So that'll give me at -4, -3.5, and -3. Not moved left or right. And then since it isn't moved left or right, that's my vertex I just plotted there. And then I can reflect across to get the other half. You might notice too that really absolute value functions are just lines with a slope that matches your vertical stretch or shrink factor. Like that one has a slope of 1/2 going up from the middle. Our previous one had a slope of 2, so you can also use that to graph these if you prefer. This is a vertical shrink of 1/2, and it's translated down 4 units compared to my parent function. On K, I edited a little bit. This is really part A, 2 times the absolute value of x, except it is translated left 2 and up 1. So I'm going to use my previous work. I like to always, on my transformations, if I can use something I already have, I want to use it. So I'm going to copy my table of values from part A, and then just change those coordinates so that everything is translated left 2 and up 1. So left 2 means, if you think about your x-axis, as you go to the left, things are getting smaller, so subtract 2 from your x values. And then to move up 1, I'm going to add 1 to my y's, and then get my new table of values for this function, and then I can just plot it. Ta-da! Alternate way, your vertex, is at -2, 1, and then its slope is 2 as you go to the right. Let's look at some square root functions for our parent function. So I'm just going to do square root of x to start with, and then use that parent function to get these two. So if I take square roots, I want to use values that have nice results out. So I'm going to use 1, 4, and 9, my perfect squares. And then this is actually negative square root x, which is just -1, -2, and -3. So it changed my signs and my output, my y values, which if you think about how that compares to your parent function's graph, it is a reflection across the x-axis, because it basically switched all the signs on your output values. It reflected across the x-axis. Part B, I just copied and pasted my parent function's points. Part B is essentially saying change the signs on your input values. So if I change the signs on my input values, I'm going to get this table of values for my function that I've got for h of x, which, if you look at them, is going to give you a function that, if you compare it to your original, is a reflection across the y-axis instead. So our parent function here is quadratic because we have quantities with our variable being squared. So I'm going to get a table of values for my parent function and then use it to do these two. So there's multiple ways you could do this, but I'm just going to use my parent function. So if I square some values here, remember this makes a parabola shape. On g of x, it's translated left 2 and down 3. So I could take my table of values that I made and subtract 2 from all of my x values and 3 from all of my y values to get my translated function. And then plot it on my graph and voila! On b, I'm going to look at it and go, okay, I need to move things right 1 unit, and I also have a vertical stretch by a factor of 2 from that multiplication of 2 out in front. So I'm going to copy and paste my parent function's points here, and then we should translate it right 1 first, working from our inside of our parentheses, and then we'll stretch it by a factor of 2. So right 1, add 1 to all your x values. That doesn't change your y values. And then a vertical stretch of 2 is going to make it twice as tall, so multiply all of your output values by 2. So in this case, actually one of those affected your x's, one affected your y's. So you could have done them both at the same time. But if you have a translation up and also a stretch, you'd have to make sure that you stretched it and then translated it like up or down. So this doesn't exactly fit on my graph here. If I plot it, it looks like that. Alright, we're going to write an equation for this absolute value function, which I would rather do than graph any day. So my vertex is at 2, 4, so it's translated right 2 units and up 4 units compared to a normal parent function for absolute value. So let's start with that when it goes time to write my equation. So I'll do f of x equals absolute value of x minus 2 plus 4, would translate it to the correct location. And then I need to decide if this has a stretch or a shrink or a reflection, so I might need something out in front there. Well, if you look at how you get from my vertex to the next point to the right, I'm going down 2 units and right 3 units. So it has a vertical shrink of 2/3 and also a reflection across your x-axis. So you'll need a negative 2/3 out in front. And here's a quick little summary of all the transformations that we've talked about.